Hello friends, welcome to our channel Knowledge Amplifier. So today in this particular video I am going to discuss one very interesting concept and very powerful concept in digital image processing domain, and that is LOG, Laplacian of Gaussian filter. Okay, what is the use of the filter, what is the mathematical intuition behind this, how to do the programming part, all these things in detail I am going to discuss from scratch. Okay, so if you have some prerequisite knowledge in filtering part of image processing, you know that Gaussian filter is nothing but one low pass filter widely used to remove noise or sudden changes present in image, and Laplacian filter is a high pass filter which is used to extract the high frequency or sudden changes in intensity level present in the image. Right now, what is the combination Laplacian and Gaussian? Let me discuss that. Okay, so if you just recall that how our edge detection works, just have a quick recap. That suppose you consider this particular image, here you can easily understand that from here to here sudden intensity change is happening, so no doubt here one edge is present, right? We can say this from visual inspection. Now how we can tell programmatically? Very simple. What we have to do, we have to get the plot of the intensity level. If we get, we will be getting like this, because it is quite clear. Initially black in the left hand side, black color means 0, white color means 255 maximum, right, in grayscale image for unsigned integer 8-bit representation. So you can see that in this particular part it is taking small value and suddenly it is going to high value. Now we have to detect the sudden changes. So sudden changes or rapid change, that means no doubt derivative from calculus part is going to help us, right? If we take derivative of this particular unit step, we will be getting delta function, which is clear from the fundamentals concept of signals and systems. And what we do now, that once we take the derivative, we decide one particular threshold. Okay, if the derivative goes at any instance above that particular threshold, okay, then we can consider that there actually our edge is present. Like here, suppose our threshold selection is this one, now derivative is going above this, so we can consider that at this particular one our sudden changes is happening, which we can see here as well, right? So this is the simple idea to understand the edges or to extract the edges. Life was so good with this particular algorithm only until and unless we encountered noise, which always present in practical situation. In our real life images, always this kind of sudden changes never appear. It will go smoothly. The change will happen little bit noisy fashion. Now you can observe here, right? Now noisy input image, if you take the intensity plot, you will be getting like this. And you know, I have already discussed in detail in my previous video that what problem you will get if you take derivative of this kind of noisy unit step signal. You will not be getting ideal unit delta, rather than that you will be getting this kind of noisy noisy amplitude signal. Okay, so now in this particular part, deciding the threshold is quite difficult for us. So what remedy I have discussed, that is, in this particular noisy signal, let us apply some low pass filter. And previously I have discussed Gaussian low pass filter, which will eliminate these noises, and as a result, after passing via a Gaussian filter, we can expect that the outcome should be like this one. Here we can directly take derivative, so derivative will go like this way, and we can take our threshold value, and according to that we can detect our edges. As simple as that. So the picture or the solution which I discussed was this one, that is, this is our original signal. We are basically convolving this particular one with Gaussian, which is basically one low pass filter, and as a result all the noises, high frequency components are removed, and we are getting this one. Now on this one we are applying derivative, and we can see here changes are happening. If we take threshold like this position, we can easily detect that here actually derivative is going above threshold. That means here actually our edge is present, right? So this is the solution. Now you can see this is two-step process. Why? In the first step we are passing the particular original signal via convolution method with Gaussian kernel. That is, we are first applying low pass filtering and then we are taking derivative. So this is two-step process. Let us try to reduce the two-step process in a single step. And how we can do that? We can use the property of convolution. what the property of convolution says. Suppose you are having one signal f and the kernel g, and you are convolving and then taking derivative. So that means what? That means nothing but this particular one. This is nothing but equation of our popularly known convolution, integration of minus infinity to infinity f of tau g of t minus tau d tau. Now as overall this one we have to take derivative, so we are writing here d dt, as simple as that. Now see, f of tau, this is function of tau, not t. So the derivative will be only applicable on this one where t is present. So we can take the derivative inside this integration and we can put like this. Okay, right? Up to this also clear. So del t of g of t minus tau we can write like this, g dash of t minus tau, that is derivative version. So this is nothing but what? Integration of minus infinity to infinity f of tau multiplied by this particular one and then d tau. That means nothing but our original signal f convolution with derivative of g, right? So we can conclude in simple words, this particular formula is applicable for convolution. That is, we are convolving to signal f and g and then taking derivative, that is equivalent to we are taking f and convolving it with the derivative version of g, right? And this particular very important property of convolution can help us to reduce this particular two-step process into one single step process. How? Let's see. So basically this is the formula which just now we achieved, and this is our previously which we discussed, which is taking two-step process. First we are using Gaussian filter to remove noise, we are getting the smooth version, then we are taking derivative to detect the edges, right? Now instead of that, what now this particular picture is proposing, try to understand. So basically here if you just consider with this particular equation, f is this one, g is this particular Gaussian one, we are taking convolution, that means this particular step we are performing, and then taking derivative, which is this particular step, right? Now instead of that, I am telling I'll be following this particular approach. F, which is our this signal, and this Gaussian, that is g, we are taking derivative of this one only. Okay, derivative of this Gaussian is this particular, okay, this particular one. If you just take derivative of Gaussian signal, you can understand in MATLAB or in Python, you can have an attempt. It will look like this, and it is quite clear. Suppose intuitively also we can say, suppose Gaussian looks like this, then how the derivative will look? See, here slope initially increasing, so it will increase, and then here see slope gradually decreasing and becoming flat, so here it will again starting reducing, then here also slope is keep on reducing, so slope keep on reducing, and then here again the reduction is decreased, that's why it will go like this. So this is basically derivative version of Gaussian which we are putting here. Now if we have this one, directly we can convolve this one with our original signal f, and that will give us the same result because this particular formula itself telling that. Okay, so instead of following this two-step approach, now in the beginning of the process itself, if we have the derivative of the Gaussian, that one itself we can convolve with our signal f, which is noisy signal, and we can get our smooth version and edge detected signal in the output, right? So see what overall happening due to application of this particular powerful formula, that two-step process is converted to one single step process. So here what we are doing, we are first applying Gaussian low pass filter, then taking derivative. Here what we are doing, we are applying convolution of our original signal with derivative version of Gaussian. Derivative version of Gaussian should be present in the beginning itself, right? That's make the whole process very simple, less time consuming, resource efficient. This is resource efficient solution which is required in real-time projects as well, right? So I hope this particular picture is clear to you. Okay, now let's come to the question, what is LOG? Why, how this particular discussion is related to LOG, Laplacian of Gaussian, how this is related? Let me discuss that. And for that, let me go to this particular handwritten note. Sorry for the bad handwriting, okay, but I hope you can easily understand. So to detect the edges, what we were doing, we were taking derivative. Okay, now we went back to double derivative. Why double derivative? If you recall why we switched to Laplacian filter, that is double derivative instead of single derivative. See, I have clearly discussed here if you observe this particular video, Laplacian filter and implementation in MATLAB, you can clearly understand this. So suppose in our particular image there is intensity change like this, then what we generally do, we take the first derivative, we get this kind of response, then we have to detect or decide one particular threshold, and if derivative changes above that threshold, that time we will understand that here actually age is present. Okay, like suppose we are considering our threshold somewhat here, so we can understand that a derivative goes up beyond that particular threshold, so age is appearing. Now the decision of threshold is very important in this particular case, because if we choose wrong threshold, then it might happen that somewhere age is present but that age might not be detected. That's why, to avoid that particular confusion, if we take double derivative, that is derivative of this derivative, we will be getting this kind of signal, right? And see, from here we can clearly understand that here intensity change is appearing, because here what is happening, the signal goes, it goes up, then it goes down, it goes here, it goes below, then going this side. Okay, so that means somewhere in this particular location zero crossing happening. Okay, and the zero crossing is ensuring that here age is present. Okay, no need to decide any threshold, right? That's what we discussed. So basically what I want to say, that from single derivative we went to double derivative to avoid that decision of threshold part. Now the problem which we encountered in single derivative, that is presence of noise. That's why this particular version is replaced by this particular version, d dx of f convolution with Gaussian filter. And this one can be written like this, f convolution with derivative of Gaussian filter. Now similarly, when we are applying Laplacian filter, then also it might happen in this signal f noise is present. So here also, before taking double derivative, we have to apply low pass filtering using Gaussian filter, that is f convolution with g. Now this particular expression, observe it very carefully how I am modifying d square f convolution with g by dx square. That means nothing but what, we have our original signal which is noisy, we are basically removing the noise using Gaussian filter and taking double derivative, that is applying Laplacian filter. So d square by dx square, we can write d dx of d dx like this. Now d dx of f of g, just now this particular part we knew from the formula of convolution, we can write like this, f convolution with g dash. Now again this particular one, again from the formula of convolution, we can write like this, f convolution with g double dash. So this is what, this is nothing but Laplacian of Gaussian. Why? Laplacian means double derivative, and we are applying double derivative on Gaussian, not on our original image. And that double derivative version of Gaussian we are convolving with our original signal. So that's why it is called Laplacian of Gaussian. Laplacian means double derivative. The double derivative we are applying on Gaussian, that is nothing but Laplacian of Gaussian. Okay, so this is the whole story. So what is Laplacian of Gaussian filter, if you are asked? That is nothing but what we do, we have one image which is noisy. To remove the noise, we apply Gaussian filter, then we get all the random spikes removed, then on that we apply Laplacian transformation or double derivative, that is nothing but Laplacian of Gaussian. Now to make that whole process more efficient, okay, resource efficient, less time consuming, what we do, instead of applying double derivative on the low pass filtered signal, we take our original signal and we convolve that with double derivative of our Gaussian kernel, and that is nothing but Laplacian of Gaussian, which we do practically. Okay, so this is what all about Laplacian of Gaussian. Okay, now let's go back to our presentation. Why LOG? It is clear to you. Now how the kernel shape? Okay, like here I have intuitively told you that if we have this particular Gaussian kernel, if we take single derivative, we can get like this. Okay, and this we can easily understand from the mathematical intuition also, just now I have told. Now how the shape will look, or how the kernel shape will be if we take double derivative of the Gaussian, which basically we are going to convolve with our this noisy original signal. Let us inspect that one. Okay, so that one I can show you using MATLAB. Okay, let's see in MATLAB. So here I have opened MATLAB online. One simple code is written, CLC clear all close all warning off. I am creating one 2D grid, and then here taking nothing but formula of Gaussian, exp of minus of x square plus y square, okay, e to the power minus of x square, the conventional formula of our Gaussian, and in 2D that's why it is x square plus y square. Now we are doing surface plot and line style, none we are giving. Let's check. So this is our nothing but what? This is going to give us our popular Gaussian kernel, which is basically used for low pass filtering, okay. That looks like this. You can apply here, rotate 3D. If we just simply hit and enter, we can apply rotation here, okay, and we can just move around and we can check. So this is our Gaussian filter, okay. Now what we need to inspect? We need to understand the kernel shape. So that's why we need to implement double derivative of this one. Double derivative means nothing but what? Double derivative means nothing but Laplacian filter. And I have told you what is the Laplacian filter equation. 0, 1, 0 in the first row, 1 minus 4, 1 in the second row, 0, 1, 0 in the third row. This derivation I have explained in detail in the Laplacian of Gaussian. Okay, if you check the derivation, here we got this particular matrix, okay. That same matrix I am taking and applying imfilter, where we are applying our this Laplacian of Gaussian, that is double derivative on our this particular Gaussian, and we are plotting that one. So let's check that one, how that particular kernel, okay, that is double derivative version of Gaussian, how it will look. Let me show you that, and that is really very beautiful, okay. We can apply rotate 3D from here as well. Just click on this particular icon and you can rotate your image, okay, and inspect the shape from all possible direction, okay. See how beautifully it looks like. Initially it goes up little bit small hill and then suddenly it goes down, okay, right. So this looks like our kernel now. So what becomes our whole story? Our whole story basically boils down to this particular picture, okay. See this particular kernel, I hope you can correlate. This is nothing but what just now I have shown, little bit small hill going up and then going down and then again going up. This is nothing but what? This is nothing but this particular one only, okay. Just cross section I have taken, right, okay. So here, so this is basically double derivative version of our Gaussian, and this one we are directly going to convolve, okay, with our original noisy signal, and then we can get this one. This one is expected, right, because Laplacian filter also gives this kind of shape only, and from the zero crossing we can understand that here edge is present. So why this whole process is required if we are already having Laplacian? The sole reason is avoiding the noise, okay, and we are doing some optimization with respect to computation also. So the whole process, again I am repeating, this is our noisy image. If we simply take double derivative, we will not be getting the proper value. That's why what we are doing, first we are applying Gaussian filter to remove the noise, and then we are taking double derivative, okay. And double derivative, you know that somewhere zero crossing will appear, that shape goes like this, which I have already discussed in the simple Laplacian filter, okay. And from the zero crossing we can understand, okay, there actually our edge is present. Now instead of doing this way, we are optimizing this. Instead of going via this whole long process, we are using the property of convolution, and we are taking double derivative of our Gaussian kernel, and that one directly we are applying on our this particular noisy image to get the filtered one, okay. And this will be our edge detected output, okay. Wherever zero crossing will appear, there our edge detection will occur, okay. Now how we can do in MATLAB? In MATLAB, to do this, the function is here. If you go below, here you can see the function is log. So in the edge function, basically the method which you have to pass is nothing but log, okay. This finds edges by looking zero crossing after filtering image with Laplacian of Gaussian filter. I have told you that zero crossing is our central idea of Laplacian filter edge detection. Now here we are applying Laplacian of Gaussian, okay. So one particular parameter you have to choose very wisely while using this particular filter, and that is what? The standard deviation of the Gaussian kernel. You know, right, that Gaussian kernel requires the standard deviation. So for that you can give this particular parameter. Here you can see that here sigma value you can specify. For log method you can give this particular parameter as value, extra parameter, okay, to control the standard deviation of the Gaussian kernel, which is used in the process of Laplacian of Gaussian. So I hope the overall story of LOG is clear to you. This is nothing but one advanced version of Laplacian filter or double derivative to avoid the noise. That's it. I hope you have enjoyed this. This is all for this video. Thank you.